Hi everyone, you might have likely used Heaps data structure in your Dijkstra's algorithm or even scheduling task. But have you ever wondered how a heap is actually implemented behind the scenes? If not, then this video is for you. Let's break it down. Okay, so before starting, I want to highlight the advantage of heap data structure. So let's assume that we have this array over here, and these are the queries that we need to perform on this array data structure, right? So the first query says that insert 8. Okay, so we'll insert 8. Done. Second query says that insert 3. Let's insert 3. Third query says that return the maximum element present in this array. So maximum element is 8. So we will return 8 over here, right? Well and good. Now the fourth query says that insert 10. Okay, we have inserted 10. Now the fifth query says that return the maximum element. So the maximum element is 10. So we will output 10. Now how exactly we are finding the maximum element? So we will basically iterate through all the elements one by one, right? For example, this pointer will go to this element, then this element, then this element, and so on and so forth until the last element. And finally, we will return the output, which is 10. So the time complexity of getting the max element in array is O of n. Okay. Whereas the same thing can be achieved in O of 1 time complexity with the help of heap data structure. Right. And this is the reason why we are designing heap. So there are two kinds of heap data structure. The first one is Min-Heap and the second one is Max-Heap. So in this video, what I'll do is I'll explain the Max-Heap in the theory section, but for the code part, I have implemented both Min-Heap and the Max-Heap. Okay. And the flow of this video would be, first we'll discuss the structure of the heap, because see, minimum heap is the heap data structure which will return the minimum element in O of 1 time complexity, and maximum heap is the heap data structure which will return the maximum element in O of 1 time complexity, right? So there must be some underlying data structure which is able to do so, right? And we will talk about that underlying data structure in this part. Then the second part is, we'll discuss the different kind of operations. We'll walk through one test case and try to see these operations like insert, remove, and peek. So peek basically returns the max in the max heap and mean in the mean heap. Okay. So let's start with the structure of the heap data structure. So heap can be represented as a complete binary tree. If you don't know what exactly complete binary tree is, let me show you that first. Complete binary tree is a special type of binary tree where all the levels of the tree are filled completely except the lowest level, which is filled from as left as possible. So basically, let's say this is the tree. This tree has 3 levels: level 1, level 2, and level 3. So all the levels except the last level should be completely filled. So indeed, level 1 and level 2 are completely filled, and the last level should be filled from left side. Okay. For example, the first node should come over here, then second node, the third node should come over here, then fourth node. Okay. So this is what complete binary tree is. I hope you got this. Okay. So basically, heap is represented as complete binary tree, and one more point is the root of that complete binary tree will be minimum for the mean heap, and it would be maximum for max heap. So currently we are designing the max heap, right? So this is the maximum node in this complete binary tree. Okay. See, 18 is the maximum among all the nodes, right? So this is the first point that you need to keep in mind, that heap is represented as a complete binary tree where the root is the maximum for the max heap. The second point is, let's say I take any node, for example, this node. Okay. So all the nodes below this node, that are these nodes. Okay. So all the nodes below 16 should have a value less than equals to 16, right? All the nodes below 9 should have a value less than equals to 9. All the node below 15 should have a value less than equals to 15. So this is what the second point is saying. Okay, I hope you got this point. So with the help of these 2 points, we can implement the heap data structure, right? So what exactly this third point is saying? Third point says that complete binary tree can be implemented using an array. So let me show you. Heap basically is represented as complete binary tree. Okay, complete binary tree, right? And complete binary tree can be implemented using an array. So indirectly, heap data structure can be implemented using array data structure. Okay, so what we'll do is we'll basically use array and code the heap data structure, right? I hope you got this point. Conceptually, heap is a complete binary tree, conceptually. Okay, but implementation wise we are using array, because array is most optimal compared to this binary tree. Okay, because in binary tree we have to have a node and we have to also have a pointer, and compared to that array does not have something like that. Array just has indexes, and coding this heap data structure with array is much easier. Therefore we'll use array data structure. Okay, so I hope this part is clear. So let's check out how exactly we are representing this complete binary tree with the help of this array data structure. Okay, so by the way, the name of this array is heap and it follows one base indexing, right? Also, you can notice that I have written some values over here which are red in color. These are nothing but the index in the array. So 18 would be present at index 1, which is over here. 16 would be present at index 2, that is over here. 8 would be present at index 6, which is over here, right? And since the root node will store the maximum element, so the first index in the array would store the maximum element. Okay, so I hope this part is clear. And the most important part is, let's say I am standing at this node. Okay, let's say I am standing at this node which is 15. Now if I want to go to the left of this node, I'll make use of this pointer. I'll make use of this pointer and reach the node 8, right? And if I wanted to go to the right of this node, then I will make use of this pointer and reach the node with value 5, isn't it? So basically this tree has some pointers so that I can go to the left and the right. But in this array, how can we go to the left and the right? Let's say I'm standing at this index, which is index 3. Then how to go to the left of this 15? So here we have certain formulas to remember. So these are the formulas to remember. If let's say I'm standing at index 3, which is over here, so left of 3 is nothing but 2 into 3, which is 6. So left of this 15 would be 8. And indeed, it is true, right? According to this binary tree, it is true. And right of this index 3 would be 2 into 3, which is 6, plus 1, which is 7. So we will go to the index 7, and element over here is 5. And again, it is true as per this complete binary tree. Also, we have one more formula, that is, we can even go to the parent as well in this array. So let's say I want to know the parent of this 5. So this 5 is present at index 7. So parent of 7 is equals to 7 upon 2. So 7 upon 2 is 3. So what is present at index 3? 15 is present, right? And indeed, it is also true. Hence we can say that array can be used to implement heap data structure, right? So now that we are confirmed with the underlying data structure, so let's start going through the different operations of the heap, which are insert and the delete. Okay, so assume that you are given one stream of integers, and the problem statement is at any given point of time, you have to tell me the maximum element seen till now. Okay, so the best data structure would be heap data structure, right? But for a moment, just forget that your programming language has heap data structure. Okay, just forget that your programming language has inbuilt heap data structure. So we will try to implement heap data structure with the help of this array. And in order to visually understand the state of this array, what I'll do is simultaneously I'll draw this complete binary tree over here. Okay. And we know that the heap data structure should follow this conditions. So we will also check the conditions as well. Right. So let's start with the insert function. So insert function has two steps. The first step is we will append the element in the array. So the current pointer is at 9. So I will take this element and append that to the array. So I have already appended to the array, and I have already created the node. This is for visual understanding. Okay. Done. Now after doing this thing, after appending, we will check the condition, whether they are violated or they are not violated. So till now they are not violated. So we are good to go. So we will move the pointer. Okay. Now the first step says that we have to append the element in the array. So let's do that. Okay, we have appended. Let's visually understand that as well. Done. Now check whether the conditions are true or not. The second condition is violated because 15 is greater than the 9, which should not happen, right? So we will call the heapify function. What heapify function do is it will swap the current value with the parent value. Okay. So what is the current value? Current value is 15. So we will swap this 15 with the parent, which is 9. So let's do that. Done. So by the way, this is the visual representation. The actual change would happen in the array, right? So let's swap the 9 and the 5. 9 and the 15. Done. Okay. Now check the condition whether it is violated or not. It is not violated. Hence we are good to go. So now let's append 8. Okay. We have appended 8. Let's also create the node. Done. Check the condition is violated or not. It is not violated, right? So let's move ahead. So the new node is 16. Let's append that in the array as well as the complete binary tree. Now, why am I appending the 16 over here? Because we know that complete binary tree will go from left to right. For any level, it will go from left to right, isn't it? We have already seen the definition. So after appending the element, you can see that the second condition is violated. So what we'll do is we'll call the heapify function. Heapify function will swap the current value with the parent. So let's swap it. Current value is 16 and the parent value was 9. So we have swapped those values. So let's swap the values in the array as well. So this will become 9 and this will become 16. Done. Let's again check the condition. The condition is still violated because 15 is lesser than 16. So we will again call the heapify function. So heapify function will basically be called again and again until we've we have fixed all the violation. Okay. So let's swap 15 and 16. Done. Let's update this as well. Okay. Now we have fixed all the violations, so we are good to go. The new node is 7. Let's append over here. Let's also make that 7 over here. Done. Is the condition violated? No. So let's move ahead. Let's append this 2 in the array as well as let's create the node as well. Done. Is the condition violated? No. So let's move ahead. Let's append this 5. Let's create the node corresponding to that. Is the condition violated? No. So let's move ahead. Let's create the element. Let's append the element. Let's create the corresponding node. Done. Now, is the condition violated? No. Let's move ahead. Now, this is the most important step where you can clearly observe the heapify function. So let's append element 18 into the array. Okay, done. Let's also create the node for that 18. Done. Now, is the second condition violated? Yes. So what we have to do? We have to basically call the heapify function again and again until we have fixed the violation. Okay. So let's swap 18 and 9. So 9 will come over here. 18 will come over here. 9 will come over here and 18 will come over here. Done. Still the condition is violated because 15 is lesser than 18. Okay. So 15 will come over here and 18 will come over here. So we have to swap 15 and 18. Done. Now again the condition is violated because 16 is greater than 18. Sorry, 16 is less than 18. So we have to swap them. So let's swap them. Done. Let's make the changes in the array as well. Done. Now check the conditions. Now the condition is not violated, so we can stop. Okay. Now if someone comes and asks you, like, tell me the maximum element, you can directly return the element present at index 1, which is 18, and it is true, right? So this is how we implement the insert function. Insert function basically follows this two step, right? So I hope you understood this insert function. Now let's check out the remove function. So this is the array that we constructed just now, and this is the complete binary tree corresponding to this array. Now the goal of this part is we have to we have to implement the remove function. Okay, this remove function basically removes the maximum element in the heap, which is 18. So it will remove the root. Okay. By the way, we have to remove this in O of 1 time. Sorry, O of log n time. So remove function follows these 3 steps. The first step is swap the root with the last element. So we'll swap the root with the last element. So let's do that. Done. Let's also make the changes in the array. So 9 will come over here, 18 will come over here. Okay. Second point is remove the last element. Okay, so we'll remove the last element. Done. Here also we'll remove the last element. Now check whether the condition is violated or not. We already know what condition we have to check. Whether the current value is greater than all the nodes below it. Okay. That is 9 should be greater than equal to all the nodes below it. So we can clearly see that it is less than 16. Right. It is less than 16. Hence there is this violation. So what we'll do is we'll try to swap the 9 with this 16. So let's do that. This is a part of heapify function. So 16 will go over here and 9 will come over here. 16 and 9 are swapped. Done. Now again there is one violation, as you can see. So 9 and 15 will be swapped again. 15 will come over here and 9 will go over here. Let's make the changes in the array as well. Done. Now is there any violation? I don't see any. So we are good to go. So we have successfully called the remove function. Now if someone comes and asks you, like, tell me the maximum element. So again, you can directly return the element present at index 1, which is 16. Okay. Now again, let's call a remove function. This is the most important part of this remove function. Please focus. So first step is swap the root with the last element. Let's do that. So 16 is swapped with 1. Done. Let's make the changes in the complete binary tree as well. Second step is remove the last element. Let's remove the last element. Done. Now check whether the condition is violated or not. That is, nodes value should be, current nodes value should be greater than all nodes below. Right. So what is the current node? Current node is 1. So is it greater than equals to all the nodes below it? No. Right. It is less than 15 and it is also less than 8. Now I need to bring this one level down. I need to bring this one level down using heapify function. Now where should I bring this one? Should I go on the left side or should I go on the right side? So I will go on the left side. That is, I will swap this one with a 15. Why? Why not 8? Because let's say I swap this with 8, then still we are stuck at this particular level, isn't it? And that's the reason why I will swap this one with the 15. Because ultimately, if you see, I have to implement this function in log n time. Hence, I need to go one level down after every iteration. Okay. And that's the reason why if I swap this with 8, then still I am stuck with level 0. Okay. Still we are stuck with level 0 because level 0 and level 1 has some violation. And that's the reason why I will swap this 1 with 15, not 8. Okay, so let's swap this 1 with 15. So 15 will come over here and 1 will go over here. Done. Now check whether there is some violation or not. And we can see that there is one violation. So again, take this one and swap with the maximum element, which is 9. So this will become 9 and this will become 1. This will become 9. This will become 1. Now again check whether there is any violation. No, there is no nodes below it, right? So we can stop. So this was the heapify function. And I hope you understood this thing. And if someone comes and asks you what is the maximum element currently, you can directly return the element present at index 1. Right. So this was about the remove function. I hope you understood the insert function and the remove function and also the structure of the heap. Like we are using the array and why are we using the array? Okay. So now let's check out the code. So I have implemented the Max-Heap and the Min-Heap as well. So let me show you the code for Max-Heap. So first what I've done is I have one interface which is heap, and Max-Heap and the Min-Heap both are implementing that interface. Right, let me show you one by one. So this is the heap interface and there are 4 functions like add, remove. This is to get the maximum element in O of 1 time complexity, and this is to check whether the heap is empty or not. Okay. So both Max-Heap and the Min-Heap will implement this heap data structure. And by the way, since I want my heap to be flexible, like it can have string data type or any user defined data type, hence I am using this generic. Okay. So let's check out the Max-Heap implementation. So what I have done is this Max-Heap is implementing this heap interface, and here you can clearly see that I have extended this type to the comparable. It means that any element which goes into this Max-Heap should have a compare to function. So for example, if I insert a integer or a string, so both has a inbuilt compare to functions because both implement comparable. I'll show you for the string. Uh, so let's go above. Yeah. So string is implementing comparable, right? And it will have one compare to function as well. So yeah, here it is. So what this compare to function does, it will basically compare one string with the another string, and if both of them are equal, then 0 would be returned. And if the first string is less than the second string in lexicographical order, then -1 would be returned, which is less than 0, and a value greater than 0 would be returned if first string is greater than the second string. Okay. So string basically implements that compare to function. Similarly, integer also implements this compare to function, and it returns -1 if first integer is less than 0. Sorry, first integer is less than second integer. It will return +1 if the first integer is greater than the second integer. And if both of them are same, then it will return 0. Okay. But if you are having some user defined data type, like let's say student data type, student class, then in that case you have to implement compare to function on your own. Okay. So I hope you understood this thing. And I will again explain, I will highlight where exactly we are needing this thing. So let's go further. So firstly, as discussed, we will use array data structure. So we are using array list, okay, over here, and the data type would be T, right? So let's start with the constructor. So we are constructing an array of size 1. Why we are constructing array of size 1? Because we are creating one base indexing. So let's say currently the array would look something like this. Now the element that we would be inserting will go over here. This would be element 1, this would be element 2. So if we see the indexing, this is the 0 index, this is first index, this is second index, right? So since we can start from this index, that's why I have inserted null over here. So I hope you understood this part. And these are the overridden function that are present in the heap interface. So I have implemented them over here. Again, this is very trivial. If the size of the array is only 1, then we can say that array is empty. There are no elements present. Okay. Because of the reason that I have explained. Since these are the main functions, I have also used some helper functions. These are the helper functions. In theory, I have explained that we were swapping the values, right? So we need a swap function which will swap the values in the array list. Okay, so this is how we implement that. This is very trivial. You can understand this thing. Then these are the formulas that we were working with. Now the main functions are up heap and the down heap. Okay, so this is called during insertion and this is called during removal. Okay, so what we'll do is we'll first try to check the add function. So I have one element that I want to add into the max heap. So let's check. So what I'm doing is I am first calling the list.add. If you remember, the first step in the insert function was we were appending the value into the array. So this is how we append the value into the array. Okay. And the second step was we have to call the heapify function again and again until the violation is not there. So we will call the heapify function from the last node because this is where we have inserted. So if I have to show that in your diagram, if we insert any value, that value will go over here, right? Isn't it? Let's say I insert 100. So 100 will go over here. Right? So I have to start the heapify function from this 100. So 100 will be present over here, which is at the last index. Hence, I should call the heapify function from the last index and I have to go upwards. Okay. So where is the up heap function? Yeah, this is the up heap function. So what we are doing is first we are checking the current value. This is the parent. This P is the parent. Okay. So we are checking the current value with a parent. And if the current value is greater than the parent, then we are calling the heapify function after swapping. So if the current value is greater than the parent, then we are calling heapify function. But before that, we will swap this, right? I mean, heapify function itself has the swapping logic. So basically, if the current value is greater than the parent, then we will call the swap function. Okay. And again, we will call the upheap function from the parent. So in other words, these values would be swapped. Okay. Now I have swapped these two values. Then I will call the upheap function from this point. Okay. I will call the upheap function from this point. So that is what I have done. I have called the upheap function from the parent. This is I have implemented the upheap function using recursion. Okay. And once we reach at the index number 1, so index 1 will not have any parent, right? So we will stop. Okay. So I hope you understood the upheap function. And this is the compare to function which is already implemented in the integer and the string. And we are able to call this because of this comparable. And let's say I remove this comparable. If I remove that comparable, then I will not have access to this compare to function. Okay. And that's the reason why I am extending this type T to the comparable. Okay. I hope you understood that thing. So upheap function is done. Now basically add function is done. Now let's check the pop function, which is remove function. Again, what we'll do is if the list is empty, if list, if this is empty, okay, if list is empty, we don't have to check the empty on the list, but we have to call this function. Okay. If the heap is empty, then we will call the null, right? I mean, we will return the null. Okay. But if it is not empty, then we know that what we have to do. By the way, in the heap data structure, we have to remove the node plus we have to return the maximum value. This is the functionality of the pop function in the actual heap data structure. So what we'll do is we'll take the maximum value and store that into one variable, and at the end we will return that maximum value. And between that, we will perform the steps. The first step was we were swapping the root with the last value. So we were swapping the root with the last value. Done. So after swapping, we were removing the last value from the list. So this was the second step. Okay. After performing two steps, the third step was calling the down heap function from the root. Okay. So let's check out the down heap function. So what we are doing is we are checking the current index. Okay. We are checking the current index value with the left child and the right child, and whichever one is the maximum, I'm noting its index. Okay, I'm noting the index of that maximum element, and if that index is the same index, right? See, what is the maximum index in these three nodes? The maximum index is, I mean, what is the maximum node? The maximum node is 15. And what is the index of that maximum node? 1. So do I need to swap this 1 with 1? No, right? Okay. But if let's say this was, let's say 0. So what is the maximum value over here? 9. Okay. And what is the index of this 9? 2. And is 1 equals to 2? No. Hence we will swap. Okay. I hope you understood now. So after swapping, the node will go one step down. So from that one step down, we will call down heap again. So recursively, we will call this down heap again and again until we will not have any children. Okay. Or this condition becomes true. So I hope you understood this down heap function as well. I think I have covered add function and I have also covered the pop function. Now let's check the peak function. This will basically return the maximum element which will be present at index number 1. Okay. So this was trivial. So now let's run this code. So by the way, I am using Max-Heap and I have created a heap which will have integers. So I've inserted some integers 1, 0 and 3 and I am printing them one by one. So it should sort this integer in descending order. I mean, it should print this integer in descending order. Okay. And I have also created one heap of string data type. I have inserted 2 strings. So again, it should print this strings into lexicographically descending order. Like S should come first, then T should come. Okay. So these are the let's run this first. So 312 is coming and Shubh and Parth is coming. Now let's say I use Min-Heap instead of Max-Heap. Okay. So again, Min-Heap is implementing the heap interface. Done. So now let's run this. Now exact opposite of this should come. Let's run this. Okay. So now 013 and P and S. Okay. So now it is sorted in ascending order. So we can say that we have successfully implemented the heap data structure. So now let's check out the time complexity for each of this function, add, pop and peak. So in worst case, the time complexity for add and pop would be log n. Why? Because of heapify function. And why it is log n? Because for the complete binary tree has a height of log n. And we are moving from top to bottom in pop function and we are moving from bottom to top in the add function. And hence the time complexity is log n for both of these. And here we are just accessing the element at index 1. Hence the time complexity for peak function is O of 1. So I hope you understood the time complexity. If you found this content helpful, then please like this video and share this with your friends. Thanks.